Okay. थोड़ा और नीचे आ सकता है नहीं? मुश्किल है.
A very good morning to everybody and welcome to this unique course on neutrons as Prof for condensed matter. I'll be speaking just for a few minutes and I will then invite our esteemed guest, Dr. Chidambaram, to share with us his perspectives, and then Professor Basu will give the first lecture in the series. But before that, I want to register our gratitude and thanks to the team, Professor Saibal Basu being coordinator, Professor Yusuf, Dr. Anil Jain, Professor Chaplot, Dr. Surendra Singh, Dr. Aswal, all of them for agreeing to come forward to deliver a series of lectures on an important subject, the neutrons as probes for condensed matter. And like all of you, I am also a student on this subject. I'm looking forward to attending all the lectures and understanding the subject to some extent. It is really a special privilege for us that today we have Dr. Chidambaram to inaugurate this course. As many of you know, of course, I know that out of the 200 participants, more than 150 are from outside. More than 150 are from outside DAE. So I take the liberty of just mentioning a few words. Dr. Chidambaram was formerly the principal scientific advisor to the Government of India and also the Secretary, Department of Atomic Energy and the Chairman Atomic Energy Commission. And earlier also as the Director of BARC, Director of Physics Group. So in several capacities, he has inspired and led the country in science endeavors. And it is very, very gracious of him to have joined today. But beyond all the positions I mentioned, most important for us today is that he himself is a pioneer in the subject of crystallography and particularly neutron crystallography. He has pioneered several efforts in BRC on this subject. So we have requested him to share some perspectives with us in the beginning. This is, I think, the best way to begin a course on neutron crystallography, to have Dr. Chidambaram with us. So it is, sir, very nice of you to have accepted our invitation. We look forward to the entire course and particularly to your lecture. Dr. Chidambaram, please.
Thank you. Thank you, Dr. Vasudev Rao. Firstly, I am very happy that Dr. Saibal Basu and his colleagues have organized this web course. I must also compliment you, Dr. Vasdev Rao, for this excellent initiative in these difficult COVID times, as we can call it. Perhaps such courses will become popular even after the COVID pandemic has run its course and gone, as will happen sooner or later. I was thinking of talking without a PowerPoint presentation, but
I will
after
just get it.
conversation with Dr.
Okay.
Vasudev Rao, I have now prepared some slides for this talk, which I'm going to display now. Shall we get to the whole screen? See, neutron is perhaps the most important particle in nuclear technology. It causes fission, starts the chain reaction needed for the release of nuclear energy. But in the study of condensed matter also, it can act as a very important probe. That is why research reactors are built. And the thermal neutrons in the reactor, the research reactor, have a near Maxwellian distribution of energy. And it so happens that the de Broglie wavelength corresponding to the peak energy of this distribution is similar to the interatomic distances in condensed matter. So it becomes a powerful tool to study the structure of materials along with X-rays and also neutrons. It also so happens that the energy of these thermal neutrons is in the same range as the energy of phonons in condensed matter. So neutron is also a very good tool for studying the dynamics of atoms in materials. Neutrons are also considered as the probe of choice for the study of magnetism because they possess spin and magnetic moment and provide a unique technique for the structural study of magnetic materials. The groups in Bach have done pioneering work in all these fields of related to neutron scattering. First at the Saras reactor, and then at the Dhruva reactor. And these groups still remain strong and very productive. If we look at neutron scattering and X-ray scattering, the main difference comes from the fact that X-rays are scattered by electrons, while neutrons are scattered by atomic nuclei. So you get, in any material, the contribution of atoms with lower atomic number is much smaller than the contribution from atoms with higher atomic number. Whereas in the case of neutron scattering, the cross section, the neutron scattering cross section, depends on the interaction of the neutron with the nucleus, and sometimes there are resonances. In fact, it may happen, it does happen, that the different isotopes of the same element may have completely different cross sections. And the most important example is hydrogen, whereas H with mass number 1 has a very different scattering amplitude than deuterium E with mass number 2. And this is very useful in an experimental technique known as contrast variation, because the isotopes hardly change the structure of a material. The structure of a material is basically determined by the interactions in which electrons are involved. And so you have almost identical material, but then if you change the isotope, substitute hydrogen or deuterium, you get a structure with very different scattering amplitudes, relative scattering amplitudes from different atoms. I'm focusing on hydrogen because, if they take the various interactions in solids, you have covalent interactions, which are very strong, which are very directional. Then you have got van der Waals interactions, which are very weak and they are completely non-directional. In between is the hydrogen bond interaction, which is somewhat directional and in strength comes somewhere between covalent bond and van der Waals interaction. And this is a very important interaction in organic chemistry as well as in biology. Take ice, for instance, in which I was interested during my PhD days and hydrates later. All the water molecules are held together by hydrogen bonds. And in fact, each water molecule is surrounded by 4 other water molecules in a tetrahedral configuration. And these interactions are all hydrogen bonds. Now, the advantage of studying them with the neutrons, because when I was doing my PhD in the Indian Institute of Science, I used the NMR technique in single crystals, in hydrates, and here what happens is the 2 water molecules interact with one another. 2 hydrogens in the water molecule interact with one another and split the proton magnetic resonance. Single crystals, otherwise of powder it becomes a little averaged out. And by reorienting the single crystal, and by changing the vector direction, you can indirectly position the hydrogen atoms and then find where are the hydrogen bonds. Of course, the chemists know, and many of you may know, the hydrogen bond interaction is interaction between 2 electronegative atoms. The hydrogen, one of these atoms, hydrogen, is connected together by a covalent bond. The other one leads to the hydrogen bond interaction. Take ice, for instance, OHO hydrogen bond. One OH is about an angstrom. The HO is about 1.74 angstrom. Of course, the hydrogen bonding will change the distances between what are called the hydrogen in the acceptor atom. Now, we had in Bach, we studied a number of crystals, amino acids, because I thought the neutron is a more direct method of studying the hydrogen position because of its, as I mentioned, the hydrogen scattering amplitude. And after hydrates, we studied amino acids, 20 or so of them are there in all proteins. And the conformation of proteins is largely determined by the hydrogen bond interaction. There, of course, we have mostly NH group and interacting with oxygen, NHO interaction. Of course, there are other kinds of hydrogen bonds. In fact, when I started the work on ice in my PhD days, I introduced the concept of bent hydrogen bonds. Because until then, they were doing only X-ray diffraction. They would know this is a hydrogen bond by looking at the distances between the electronegative atoms, and will just place the hydrogen on the line between the 2 atoms. And obviously, hello? Are you able to hear me?
Yes, sir.
No, there was some disturbance.
You can
No,
continue.
here. Here, when I said in ice, the water molecule is surrounded by 4 other water molecules. The angle is tetrahedral. The valence bond angle of in water molecule is 104.5 degrees. And one knows it takes a lot of energy to bend a covalent bond angle. Whereas I showed it is very easy to bend a hydrogen bond. So the concept of bent hydrogen bonds I introduced, which is now, of course, all hydrogen bonds are more or less, except in some cases, they are non-linear, and of course, this is now becoming also very popular to combine hydrogen and neutron studies together. My friend Philip Coppens from Buffalo in the old days. See, you get the nuclear position by studying the neutron diffraction. You put a spherical atom around it. Now you take X-ray study and find out the electron density distribution. You take a difference map for any covalent bond. And then you can see how the bond distorts the electrons around the atoms. And what Philip Coppens did was to use this to confirm the predictions of quantum mechanics. I'm talking of very, very early days. And this is combination of neutron and X-ray scattering is becoming more and more popular. And in fact, last June, we had a 47th National Seminar on crystallography held in Bach, June last year. And it was jointly organized by the Indian Crystallographic Association and the Neutron Scattering Society of India. In fact, Dr. Yusuf took the initiative for this on behalf of the Neutron Scattering Society of India. Now, we have excellent facilities for both neutron and X-ray studies in DAE, the Dhruva reactor in Bark, and the synchrotron radiation source Indus 2 at RRCAT. We have also got access to pulse spallation neutron sources in Rutherford Lab, UK, the ISIS, where in fact Dr. Dasanacharya from Bach built a day zero facility. That is when the facility, it's a spallation neutron source. It's not a fission neutron source. Spallation occurs when you take something like a 1 GeV proton and hit a heavy element with it. The neutrons kind of boil off from that. That's called spallation. And you can surround it with the hydrogenous material and you can get thermal neutrons and use it as a source. Usually these are pulse neutron sources. Similar facilities in Oak Ridge National Lab, USA, and these facilities have been used by our scientists. And similarly, we have access to the more advanced synchrotron radiation sources like the argon photon source at Argonne National Lab, USA, the photon factory in Tsukuba, Japan, and Electra in Trieste. In fact, my colleague Dr. Milan Sanyal from Saha Institute of Nuclear Physics and others have built beamline instruments there. Atomic scale, elastic and inelastic. The difference is elastic, you don't lose energy of the neutron. Inelastic, you lose energy. That's how you look at the dynamics of neutrons. Atomic scale, elastic and inelastic neutron spectroscopy has provided physicists with an excellent tool to study things like spin structures, magnetic excitation spectra, soft modes, and critical dynamics at magnetic phase transitions. It, in fact, not possible with other experimental techniques. And the good thing is the magnitude of the cross section for neutron magnetic scattering is similar to the cross section of nuclear scattering by short range nuclear forces and is large enough to provide measurable scattering by the ordered magnetic structures and electron spin fluctuations. Of course, one can also use small angle neutron scattering. I'll come to it in a moment. And SANS data have begun to be collected using polycrystalline samples. And you can use it to determine the relevant scales of magnetic correlations and magnetic correlations. Now, in this course, of course, you will have a course of lectures by S.M. Yusuf on magnetic neutron scattering. Then you have magnetic neutron scattering. Then you will have lectures on inelastic and quasi-elastic neutron scattering. You see, the dynamics of a system depends on the interatomic and intermolecular interactions, which of course are responsible for the properties of materials. And neutron scattering an excellent way to study this dynamics. While elastic will give you indirect information by locating the minimum of the potential, inelastic reveals information on the shape of the potential and much more. BRC groups have been very strong in this field over the years. And then we have quasi-elastic neutron scattering. Here, the energy transfers are very small. The limiting case of inelastic neutron scattering and includes things like Doppler broadening of the elastic line. When you got smaller energy transfers, you don't get a new line, but you can broaden the existing diffraction line. And it can quasi-elastic neutron scattering, QENS as it is called, probe slow dynamics like translational diffusion, molecular reorientations, and relaxation processes. I would like to add that in a recent paper from Japan this year, they have studied the dynamic behavior of hydration water in phospholipid membranes. Very difficult to study this. And they used various techniques, and they found that quasi-elastic neutron scattering is the most effective method for this purpose, because you can study the dynamics for both the water molecule and the lipid molecules. And of course, they used selective titration. And then we have quasi-elastic. Then we can have other kinds of studies of relaxation processes, and inelastic and quasi-elastic scattering lectures will be given in this course by Dr. Chaploth. Then you have small angle neutron scattering. See, as I said, you can locate the positions of hydrogens by neutron scattering, light atoms, which you can't do by X-ray scattering. But the number of atoms goes up. In fact, if we include atoms, the number of atoms that you have to look at doubles almost compared to what an X-ray guy has to study. So large molecules, biomolecules, are usually not studied by using neutrons. One advantage is neutrons had a very little wavelength that can be provided by synchrotron radiation sources. So techniques like anomalous scattering, going close to the absorption edge of any atom to solve what is called the phase problem in diffraction. That is, you measure only the intensities of the Bragg peaks. You don't measure the amplitude and the phase. And in fact, the most difficult problem in crystallography is to solve this phase problem. But small angle scattering can give you very important information, which is very great interest in biology. It may not tell you where the atoms are on an atomic scale, but it can tell you it's a monomer, or is it a dimer, or is this drug molecule, is it getting attached when you have a druggable targets when studying biology in drug design, is it getting attached? And I'm very happy that recently the structural biology group of Dr. Vinay Kumar and the small angle scattering, neutron scattering group of Dr. Vinod Aswal have come together to study the structure of biological macromolecular systems. And here they use the HD contrast variation method. As I mentioned, the scattering amplitude of H and D are different. Not only that, because of resonance effects, the scattering amplitude of H is negative and that of D is positive. In fact, any group, you can put a suitable combination of H and D so that you can make a atom disappear. Or you can totally titrate it and change the scattering amplitude. And this method can give you a very powerful technique to locate the positions of important groups in biological atoms. Of course, you can also use SANS, as it is called, to study other problems. I remember Dr. Mazumdar in the older days using it to monitor the degree of homogeneity of a composite cement matrix upon immobilization of low-level, non-heat generating radioactive waste. This was actually simulated cerium waste, and you will have lectures on small angle neutron scattering by Dr. V.K. Aswal. And then, of course, there's another interesting technique. Thing. Anyway, this slide. See, there's another interesting technique called polarized. Sorry for the interruption, Dr. Vasudeva. Is it okay now? Hello?
Sir.
Okay.
Yes, it's okay.
I'm coming to the end of my talk. This is a polarized neutron reflectometry. So you can take a look at grazing incidence, and you can measure the reflected intensity from the surface of a layered structure. Q is equal to 4 pi sine theta by lambda. Of course, this slide slightly got corrupted at near grazing incidence, and you can reveal information at nanometer length scale. Thickness, density, roughness, and you can also get magnetic moment density. I remember some years back Dr. Saibal Basu telling me about the work in Bach on the reverse surface magnetization in electrodeposited cobalt film and the location of a magnetic dead layer in a ferromagnet due to tunneling of Cooper pairs. And Dr. Surendra Singh will talk about this. So as you can see, there are this neutron scattering as neutron as probe is a very powerful technique, and in fact it need not be the main area of study for many people. They will find as they do their own work that there are issues, whether it's magnetism or in surface structures or in hydrogen bonding in biological molecules or whatever, where you can use neutron scattering as a supportive study for your own research work. And I'm very glad this course deals with almost every aspect of neutron as a probe for condensed matter. And in all these areas, there are strong groups who have been, and the speakers themselves here have been personally involved in these research programs. I wish the web course all success. Thank you. Thank you. I'm through, Dr. Vasudeva.
Thank you, Dr. Chidambaram, for an excellent overview of the subject of neutron scattering, a comparison with X-ray scattering, and the applications and various domains where this can be used for studying materials. I think in 15-20 minutes, you have summarized the entire course under various aspects of the course. We are very, very grateful to you for joining us today. And now may I request Dr. Saibal Basu to give the first lecture in the series. And just as one announcement to make, that from tomorrow, the lecture programs will be in the afternoon. Not tomorrow, next program. I think Dr. Saibal Basu will announce the lectures. Okay, Dr. Saibal Basu, please.
Hello. Good morning, my colleagues. And onset, I must thank Dr. Chidambaram for such a lucid description of the entire field and overview of the entire field in such a manner. I am thankful to him for delivering this inaugural speech for two reasons. One is that he had been my teacher in BRC training school when I joined. And secondly, he is one of the pioneering groups in single crystal neutron diffraction. And I remember that the first computer-based single crystal neutron diffractometer was operational inside us when I joined. I must also thank my co-lecturers. Actually, the course was coordinated, planned by myself and Professor Yusuf. Dr. Professor Vasudev Rao had been always very supportive. And we have excellent speakers for this course. After I give the first portion of the course, the introductory lectures, there is Dr. S.M. Yusuf, who will be leading the diffraction lectures. Then Professor S.L. Chaplot, who is a well-known expert on inelastic neutron diffraction, followed by Professor V.K. Aswal, who is the coordinator for the small angle or SANS part, and followed by Dr. Surinder Singh, who will be taking care of the polarized neutron reflectometry part. This is the structure of the course, and I welcome all the people on the other side of this lecture, of this screen, who are waiting to hear. So let me begin by saying, before I start the course, I need to give you some instructions. I will request you to follow these instructions. First is that, I think you already know this, a login username and password was emailed to you. So at www.anuvidya.in, and there the link for each and every lecture will be provided. So only registered participants may join the lecture. So please use the link given at www.anuvidya.in. Most importantly, participants requesting for attendance certificate, they need to attend at least 75% of the lectures. Similarly, students requesting credit for the course, they should attend 75% or more, submit their online assignments, and appear for the final test. The form of the test I haven't decided yet, but I'll keep on uploading the online assignments at the site of your login, www.anuvidya.in, and you can download the thing, and one email address has been created for this talk. I request you to, this email address is there, newcourse@gmail.com. This will help you to the assignments, and you can also send your assignment to this address. Please keep your audio and video muted during the lecture. All participants should mention their name, status, and affiliation in chat mode so that we know who are the people who have joined. And apart from this, I think now I'll get into the technical part of the talk. Please join me. I'll be going very slow. So, this, as you already know, the plan of the course is that there will be 4 modules. The first module will be introducing to neutron scattering. This is important to understand the following modules. So I will be taking this portion and describing you the neutron scattering formalism. I will go slow, and I understand that most of you are from physics background. So this portion demands that at least you have some knowledge, or you have got the scattering, quantum mechanical scattering theory. But still, I will try to go very, very slow, and I'll do the hand holding so far as the scattering techniques description is concerned. And I will request you, in case you have any queries, any problems, please, one, you can contact through comment mode here in YouTube Live. Second, even after the lecture, you please send your queries to neutroncourse@gmail.com. In the next lecture, I will try to answer them. So after the formalism, the next portion will be a module of 10 lectures. There will be microscopic structure, atomic level structure. So it will be single crystal, powder diffraction, liquid and amorphous diffraction, and most importantly, for many of you, magnetic neutron diffraction. Possibly neutron is the only technique which gives you magnetic structure at the microscopic level. This will be followed by dynamics of phonons, magnons, diffusion as described by Dr. Chidambaram. This portion will be taken by Dr. S.L. Chaplo, followed by 2 shorter modules. But I think we cannot ignore these modules because these are extremely important and popular techniques in today's world. The mesoscopic structure, SAN, small angle neutron scattering. This is for mesoscopic structure where you look at conglomerations at nanometer length scale and not at atomic length scale. And this is extremely important and possibly the grazing ground for physicists, biologists, metallurgists, and many others. This is followed by a module on polarized neutron reflectometry. Again, thin film research is extremely important these days, especially magnetism in thin films has extremely important role in fundamental work as well as for applications in memory devices and so many other devices. So this module will be taught by Dr. Surendra Singh. We do have a polarized neutron reflectometer, possibly the last instrument added to the panel of instruments that we have in Dhruva, and this will be the last portion on polarized neutron reflectors. This is the structure of the course. This is the first lecture. So this is, I hope you will be able to follow it, and also this will be a learning process for me because if there are any hiccups, please excuse us because this is for the first time we are providing an online course to such a wide audience. I hope it will not disappoint you. A little bit of history, just shortly, that neutron came in to the world like it's a neutral particle, very silently. Actually, a short paper, a very short paper in Nature, just one column in which Chadwick in 1932, he mentions that a new particle, most likely a new particle has arrived in this world, which we can call neutron. It was actually Rutherford's prediction, and this comes in a short paper because the experiment was done earlier by others like Juliet Curie, but Chadwick was the first one to identify the particle. The credit goes to him. So this is a particle which has got a mass almost like proton, chargeless. It has got a spin half with a magnetic moment of minus 1.91 nuclear magneton. So this is a particle which is neutral. So immediately you can see that we can go deep inside material using this neutron. To consider all other probes like X-rays, light. Light, of course, it can go through transparent mediums, but not all medium. X-rays penetrate typically around micron length scale because they are charged, they interact strongly with the charge in the material. So I'm just giving a timeline. So very fast, neutron was discovered in 1932. Fission was demonstrated by chemist Otto Hahn in 1938. Imagine the first nuclear reactor came just within 4 years, made by Fermi, Chicago pile under a baseball. First nuclear explosion, 1945. First nuclear power plant came in 1951. It's that fast. But today, I am going to talk about the nuclear research reactors which came up to study the structure and dynamics of material around 1950s. So in that respect, research reactor Dido came in the UK, Canada came in 1947, BNL in USA 1959. I must point out that Apsara in 1957 became critical. So the field when it was mentioned, and as I told you earlier also, Dr. Chidambaram comes from a generation which generated, not only designed these instruments, formalism, and was at the did world-class work. Dr. Chidambaram's group worked on amino acids, world-class work using neutron crystallography. So to start with, nuclear thermal are something which you find in a
I think we have to hold for a moment because I find on YouTube many comments. I also don't see this slide at all here. You can see there's some. Just wait for
I see.
That's yes. No, this unmet connectivity is same, but maybe VRC bandwidth they're providing. When does it say extrude? Something else there. Eh?
Hello. Sorry for this hiccup. So I will start once again. So as I was telling you, the story that today we'll be discussing about the use of neutron for study of condensed matter. So this is about using neutron for structure of material. There is some small delay. Yeah. So as was mentioned earlier also, Professor Chidambaram, thermal neutrons and cold neutrons, energy in the range of 1 to 500 millielectron volt are available in these thermal reactors. When I say, and they have an ideal and unique probe of microscopic structure and dynamics because their wavelength typically in the range of 1 angstrom. It can be 1 angstrom, 4 angstrom, 5 angstrom, but in the range of angstroms. And many length scales in condensed matter are matching with this wavelength. So this is also true for X-rays. What made Lave think that whether we can do diffraction. So it makes it ideal tool for structure, or in general, if I may say, for diffraction. In addition, the energy of these neutrons are quite low. Unlike a 1 angstrom X-ray, it may have an energy of tens of kiloelectron volts, but this neutron has the energy of millielectron volts. So I will like to explain this to you, that neutron coming from a reactor, actually in a thermal reactor, there is something called a moderator. This moderator brings the energy of the neutron from megaelectron volt down through ping pong ball collisions. So these neutrons, when they're cooling down, it thermalizes with respect to the nuclear moderator, and ultimately they have an energy distribution which is at the temperature of the moderator. So typically this is a Maxwellian distribution with a peak around 30 millielectron volts, and in this Maxwellian you have a portion which is typically, we say, neutron energy less than 5 millielectron volt, and that gives us handle for using them for very, very slow dynamics. At the same time, we also have neutrons which are called hot neutrons. They can be used to understand structure at very short length scales or reasonably high energy excitations in solids. So we use one particular energy in our spectrometer. We choose a particular energy in the spectrometer that we design. This energy is chosen from a beam of neutrons, and then it is made to impinge on a sample. So typically it looks so the source of these neutrons predominantly are reactors. So we have right now the research reactor Dhruva, which is located in Trombay, Mumbai. The best research reactor run by France, Germany, and Britain at ILL Grenoble. We are planning for a high flux research reactor, HFRR, which will come at the east coast of the country. Also, in addition, these days there are proton accelerator based collision neutron sources. So these are accelerator based sources. So these are pulse neutron sources, and the spectroscopy is different. I will discuss it later. So we have reactors and you have accelerator-based neutron sources. So this is how it looks inside Dhruva reactor hall. Now here you can see why can't I go back? Oh, sorry. So here, this is the wall of the reactor. This is a cylinder of outer diameter like 20 meters. The actual reactor core is at the center of it, and neutrons, there are neutron beam lines. Neutrons come down to these instruments, go out through this guide hall, they come down through these beam lines and impinge on your sample, and then we have neutron detectors all around. Typically, this is how neutron nuclear reactor hall for research reactor Dhruva looks like. Similarly, yeah, this is the experimental neutron hall of ICIS, Rutherford Appleton Laboratory at UK. There is a Spallation neutron source in which a neutron beam bombards a target like tantalum, generates lots of neutrons, not through fission, but through a reaction called spallation. And these neutrons are born with very high energy, and these neutrons are brought down in their energy using a moderator similar in a reactor, and this pulse neutron beam is sent to different experimental facilities, like you can see here. All these experimental halls, all these experimental lines are there. For example, you can see one beam line here, one beam line here, one beam line there. So they look like huge industrial facilities, but the working principles are based on pure physics and the design also, and that is what we are going to discuss in this course. So just I will get back to this later. It is just I'm trying to show you the plan of the nuclear reactor Dhruva. So this is the plan of the reactor Dhruva, in which I show you this is the core of the reactor, and we have created holes drilled through all the shieldings reaching up to the core, so that the neutrons can come out from these beam lines. They can come out from these beam lines, and our spectrometers are built outside the biological shielding. So spectrometers are built here, and for various purposes, and the purposes will be discussed. Like there will be diffraction spectrometers, there will be inelastic neutron spectrometers, there will be small angle neutron spectrometers, there will be polarized neutron reflectometers. And actually, I wanted to show you that we also have something called, very interesting thing, neutron guides that carry neutrons out by 30-40 meters from the reactor hall. And we are allowed to build instruments. I'm sorry, my hand is wobbling. It's a straight path of the neutron. And we have a small angle neutron machine here, a polarized neutron reflectometer here, and another small angle neutron machine here. So we can build instruments inside the reactor hall and also in guide tube laboratories. And in these days, you find large guide tube laboratories where instruments are built routinely. So Again, back to thermal neutrons, let me emphasize, wavelength is close to interatomic distance, as I told earlier, as energetic as atoms and molecules in condensed matter. Its neutron, that's a very big advantage, gets deep into the sample. And there is contrast between isotopes and neighboring atoms in periodic table. This was mentioned by Dr. Chidambaram. This is a very important technique, especially later when Professor Saibal will be talking about small angle neutron scattering. He will touch upon this in more details. An important thing is that there is a magnetic spin associated with the neutron. So this is useful for magnetic materials, especially microscopic or mesoscopic magnetism. Microscopic magnetism is done by using neutron diffraction, which is similar to X-ray diffraction, for which many of you will be familiar. It's a non-destructive characterization, importantly. And of course, another interesting thing is this part. As I told you earlier, that the neutron scattering cross-section, scattering amplitude, it goes zigzag over the periodic table, unlike X-rays. X-rays, they follow Moseley's law. Yeah. X-rays, they follow Moseley's law and vary systematically across the periodic table. So it goes as Z minus mu Q, if I remember it correct. Unlike that, because neutron interacts with the nucleus and the interaction depends on the neutron spin and the nuclear spin, so it can vary between the two isotopes. And there are contrasts, for example, between hydrogen and deuterium, or between nickel 62 and 60 and titanium, which is negative. So we have materials with negative scattering length, we have materials with positive scattering length. Most importantly, the scattering cross section is quite strong in the lower side of the periodic table. We know that X-rays, using X-rays, you cannot see low Z materials. Actually, almost up to oxygen, you don't see anything using X-rays. Whereas neutrons are scattered by low Z material. Actually, hydrogen is a very strong scatterer of neutrons. So hydrogenous material, or sometimes selectively deuterated material, they can be used in neutron scattering, whereas these material or these atoms cannot be detected using other techniques, most importantly using the X-rays. So now I will get into the basics of neutron scattering. So in principle, it's a very simple technique. If I see, you have an incident neutron beam of certain energy falling on a sample. A sample is a conglomeration of atoms, molecules, and there is structure in it, local structure, global structure. By global structure, I mean crystallographic structure. At the same time, there are structures which are, for example, precipitate or agglomeration of micelle. These are mesoscopic structures. So there is structure and dynamics in the sample. We have an incident energy and momentum. How we do it? So we choose from a polychromatic beam of thermal neutrons a beam. So how do we choose it? I'll just try to sort of quickly tell you. a polychromatic beam of neutrons So a beam of neutron comes out from a reactor. This is polychromatic. So there are many lambdas. Usually what we do, we have a single crystal in its path. So it scatters out a particular wavelength of neutrons, which is 2d sine theta is equal to n lambda. So using a Bragg crystal, we choose one particular neutron energy and impinges on the sample. This story may be slightly different when we talk about time of flight spectroscopy, but right now I will not load you with that. So this is the scattering process. So, and once the neutron is scattered by the sample, it is detected in a neutron detector. In this scattering process, there are two things happening. One is change in momentum energy. This is important for all of us to understand that we are studying material through a scattering process. So we will be, all our experiments, whatever I am going to talk about, is in q omega space. Momentum transfer is h cross q, and and the energy transfer is h cross omega. So basically, we are trying to map our sample in q omega space, and I'll get back to it later. And from here, we will try to get ideas about the structure and dynamics in the material, which is right now I must say it's the Fourier space of this q omega space. And what we see actually, either we see d sigma by d omega, that is neutrons per unit solid angle without bothering about energy, or we see d2 sigma d omega d, which is neutrons per unit solid angle per unit energy interval. So that means I will be measuring the energy of the outgoing neutron, and that will be for dynamics of the material. Here that for an elastic experiment, by elastic I don't mean elastic classical sense. By elastic we mean elastic as when there is no energy transfer between the neutron and the sample. In that, if you don't consider that energy transfer, then for an elastic experiment, for an angle theta, this is 2 theta. If I consider that the wave vector transfer is given by q is equal to 4 pi by lambda sine theta. Now I have put a question mark here because I leave it to you for a crystallographic, for a crystal, for an arranged atomic system, what this q should be, we all know. I'll come to it later. So let me try to derive a general expression Neutron scattering cross section. So it is elastic, so I am not talking about any dynamics in the system. If n is the number of is the flux of neutrons incident on the sample and neutron scattered inside a solid angle, so So basically, this is a simple geometrical constructions where neutron comes in this direction. There is a target, and I have written down the polar coordinates as r theta phi. It goes inside of a detector here, which is making an angle theta with respect to the z-axis and phi with respect to the in the horizontal plane. All of you know this will be this expression where the solid angle is given by sine theta d theta dm. It's fairly simple to understand. So now I'll use an expression which is known as Fermi golden rule. I will go slow here and explain term by term, but I think those of you who are done masters in physics, they will be very much familiar with this expression, and those who have not done masters in physics or unfamiliar, I will tell you that this is nothing but a transition probability. So here under is a quantum mechanical expression for a system which is initially having a wave vector psi k. When the momentum vector is k, it undergoes a change in scattering and goes to psi k prime under the influence of this potential. This is what the sample provides, the potential, the scattering potential. With this is the transition probability given by Fermi golden rule. It is basically an integral in which you so basically it is related to this is the transition probability from a state k given by this integral, apart from a few constant terms which you have written. You may, for the time being, you may just accept them. So this is the transition probability which is given by d3r. This is a three-dimensional integral. D3r, basically this r is a vector, and there is a density of states for the final state. That means if it is a free neutron, then this is nothing but d3k de, number of unit k in a volume element d. So this is the transition probability given by a small volume in k space that gives you the transition probability. And as I told you earlier, that this incident wave function is a plane wave function. We create it that way. We make a neutron beam, a parallel neutron beam, so I can represent it by a incident wave vector. Rho k prime e is given as, this is basically, if I may write it, I'll go very slow here and understand this thing. So one is the psi for a plane wave. This is because this is when I consider my sample to be a box of side L. So this is a normalization term. This is a plane wave function. And as I wrote earlier, the transition probability is given by sorry, I will write about again. Now this rho K prime E is given by this term comes because for box of side L, you have one K value in 2 pi by L. So density is L by 2 pi, and because there's X, Y, Z directions, so it is L by 2 pi Q. And then comes the term D3K DE. Now this is the D3K is the elemental volume in K space, which is given by K square phase space dk d omega. This is D3K. And when and here also I use the thing that dk by de I will obtain from for a free neutron E is equal to h square k square by 2. So if you plug in all these things in it, then I get rho k prime E equal to m k by h cross square L by 2 pi q and d omega. This is what I want to show you. So now I'll get back to my transparency. Yeah. So ultimately we try to evaluate this expression, and over here I must mention you before I go any further that often this integral I'll be denoting with similar integrals like Dirac's bracket notation, where k prime vk is basically d3r. I mean, this is a three-dimensional integral psi star k prime vr psi k. This integral is given for us, for physics people it is quite common, And for most of you, it's a repetition, but for some of you, if it is new, accept it and we'll go ahead. So once I get this rho prime, what I get actually, and the flux of neutrons is nothing but velocity by L cube, volume of the thing. So H cross K by ML cube, psi I have given. So ultimately, I get an expression for d sigma. So this is, I am calculating for a system where I have not considered the dynamics. To start with, I have got a static system in which I am trying to evaluate the neutrons scattering per unit cellular angle for a neutron of incident energy and wave vector k. And this is the expression I get finally. I'll be uploading this talk in the site, so you can download and have a look at it. Any queries, you please write back to me. So actually, I get an expression which is fairly simple, which is d sigma d omega. That means this is the neutron scattering cross section per unit solid angle is given by this expression m by 2 pi h cross square and then this bracket notation. Basically, this is the fun of quantum mechanics, that you calculate the amplitude and then you square it, you get the probability. So we always calculate probability amplitude and square them to get the probability. And when I use this as kk prime, then I can write d sigma by d omega equal to f kk prime square. Here I would like to mention one more thing to you, and that is when I say k psi k prime psi k, that means this will be looking, if I break them up, it will look like k psi k prime psi k. So I can move around these things and sort of find out the square. So this is how we work with this square. So please remember this, that this is a square in which you have to actually, two integrals are multiplied and each integral looks like this. One is the complement of this, because one will be the, you have to take a complement of this thing. That's how it, that k prime psi k becomes k psi k prime, and the other is integral itself. So it is like a complement of a, complex conjugate of a multiplied by a. So if you remember this, all our future tasks will be pretty simple. So we have derived the scattering cross section d sigma d omega, which is a square of an amplitude, basically f star kk prime f, that will give us the scattering amplitude. But so far it has been only some bit of jargoning and mathematics. What do we get from here? Now I will define the neutron nucleus interaction potential. Now, in case of thermal neutrons, the neutron wavelength, the de Broglie wavelength, is of the order of angstrom. Few angstrom, fraction of an angstrom, but of the order of angstrom. And the nucleus, the size is femtometer. It's around 10 to the minus 5 angstrom. So Fermi saw this and he introduced something known as Fermi pseudopotential. So basically, for the neutron impinging on your sample, the potential is a delta function potential. It's a delta function potential, and then we represent it by a delta r minus r if nucleus is sitting at r, then this is the delta function potential. This is known as Fermi pseudopotential because this is an approximation and recognition of the fact that the neutron interacts through strong interaction with the nucleus, and the nuclear dimension is much smaller than the wavelength, the de Broglie wavelength of the neutron. Now, when if I put it as here as delta 0, if I take only one nucleus which is sitting at the origin and put it in expression for the expression for d sigma d omega, which is this expression, I put a delta 0 here, then what I get is this d sigma by, and of course I have put a constant term 2 pi h square by m simply to get rid of the m by 2 pi h square. I get d sigma by d omega as b square, or sigma is equal to 4 pi b square. Now it is tangible. So basically, this scattering gives me the scattering cross section, a quantum mechanical scattering cross section, which is given by 4 pi b square. Classically speaking, if I put a disk of b radius in the path of an impinging beam, it will provide a scattering cross section which is equal to the area of the beam, pi b square. Quantum mechanics only adds a 4 to it. So for a single scatterer, it will be 4 pi b square. And that's what the scattering length is all about. So using, let me again mention it to you. So I started Fermi golden rule for a scattering process in which without any energy exchange, the neutron goes from k to k prime. The expression is this. Then a little bit of where I put the VR as a delta function potential, as I explained sometimes back, because the nuclear dimensions is much smaller than the neutron wavelength, and the density of states I calculated using d3k by dE, which is the density of states for a free neutron at an energy E at a wave vector k prime, and just plugged in a few things, and I get for a single scatterer a scattering cross section of 4 pi b square correctly. So for systems that we will be studying, this b is an important factor, and this is what for a single scatterer. The next problem I would like to deal with for a rigid lattice. For a rigid lattice, this same expression, now I have the scatterers sitting in a lattice. So there are atoms or nuclei, they are sitting in a lattice. It's an arrangement of lattice structure where one of them possibly, this is the, sorry, so for a arrangement of atoms, one particular lattice point, if I call it L, then I can consider the lattice as a summation of delta functions sitting rigidly, and each side has got a scattering length of BL. That means if I took it out and consider an individual atom, it would have given me 4 pi b square. Now, these atoms are sitting rigidly at sites L, but this part I'll be tackling in the next lecture. Today I have just given you the first part of the formalism for a single lattice point, and next lecture will be, I'll be dealing what I get for a rigid lattice for a neutron of wavelength k. So I'll stop here. I will take questions if any through the comment mode, and also I'll request you to send me your queries to neutron course @gmail.com. Most importantly, please remember the next lecture will be again at 11 o'clock on 7th of October. But otherwise, most of the lectures have been scheduled for 3 o'clock in the afternoon. The complete schedule for October is at www.anuvidya.in, and you can go there. The link is also there. Just clicking on the link, you'll be joining the meeting. So most of the lectures have been scheduled for 3 o'clock in the afternoon, but due to some unavoidable reasons, 7th it will be on at 11 o'clock in the morning. So I hope it's clear to you whatever I've been trying to explain. I'll go further ahead in the next lecture, and I'll see if you have any queries right now. Otherwise also, I'll be replying to your queries if you send them by email. Queries?
We'll wait for it. I will watch it.
Yeah, Dr. Saibal, this is Satyam.
There must be something, some wrong. Please tell me. Correct.
Saibal, this is Satyam. Dr. Basu.
Are there any comments from anybody? I think they can send the queries if they want by email also.
Dr. Basu, can I speak? Dr. Basu, this is Satyam. Can I speak?
What will be the arrangement?
Hello.
No, for the others to see. Yeah. So we will upload the recording of today's lecture on the Anuvidya website. YouTube channel. Okay, fine. Then they can again, because if in case they missed in between because of some connection or whatever, they can go through the entire lecture on the YouTube channel. It will be available, is it not? Okay. So then we come to the end of today's lecture. And thank you, Dr. Saibal Basu. Then next lecture is on 7th at 11 o'clock. Okay then. Thank you.
So that do you have a team?
Yes.